Good morning and welcome everyone. This is lecture number 12 on circular dynamics. Do you recollect what we were doing in the last class? What we were discussing in the last class? Tell me.
So we have discussed a problem, sir, on auto circle.
We discussed a problem on vertical circle. That is what you're saying? We were discussing problem or we were seeing outer circle, right? We were discussing problems on outer circle,
Yes, sir. Yes, sir.
and we had seen that
Finding
that
theta and v.
yes, we had seen that that motion is not confined to a circular path.
Yes, sir. Yes, sir.
When you drop it, when you push it from the top, at some point it will leave contact
Yes,
because
sir.
the velocity becomes so much that it will not be able to continue its circular path. Yes or no? Do you all remember this?
Yes, sir.
Great. Now, as I told you that we will be discussing this circular motion, this motion in a vertical circle under various headings. Right now, what we are doing is we are, and again, you might not find this in any of the books that you all have. Very rarely the books will cover everything and make it clear that what is the difference between this and this. And most of the students, my 20 years of teaching, I have realized that most of the students, they don't understand the difference between the two terms. What are the two terms? First term is motion not confined to a circular path, and the second term is motion which is confined to a circular path. The example that we did, motion on the outer surface, that was the example of motion not confined to a circular path. So this body that was kept on the top of this sphere or cylinder, it was not attached to the cylinder. It was just kept on the top, and when it was falling down, at some point it will leave contact. And we have seen at which point does it leave contact. If I just give it a very gentle push, I don't give it any velocity, a very gentle velocity, at what point does it leave contact?
2/3 of 2/3.
Yes, when it makes an angle of cos inverse 2/3, it has to leave contact. With what velocity does it leave contact?
The velocity of root over g rg cos theta.
How much is cos theta? Cos theta is 2/3. What I see on the last bench? What is happening on the last bench? Boys, what is happening on the last bench? Can I have some update? Is there something good going on? I would also like to participate in that. Can you update me on this? Are we good? Are we good to go? Bacha, are we good to go, or do we need any more? Good to go? Okay. I lost what I was telling you. I simply lost it. See, once my brain goes on to something else, on to seeing what you are doing in the class, my brain just disappears. My thought process just okay. I was asking you about the velocity. With which it leaves contact, and the velocity is root over gr cos theta. Value of cos theta is 2/3, so it becomes root over 2/3 gr. Correct? That is the velocity with which it leaves contact. Now, that was the case of motion not confined to a circular path. But the same question, same scenario, same thing could be asked in a different way, where I can attach it to this. I can make it a roller coaster, and I can attach this body to this cylinder by means of rails or something of that sort. Then it becomes a question of motion confined to a circular path. And as I told you in the previous class, then since it is attached to this circular path, so the circular path would be like this, and there will be rails like this, so it is attached, so it cannot leave. It is just like a bead in a ring. It cannot leave the circular path. Then that question becomes different. because now it cannot leave the circular path and the motion is confined to the circular path. So we will discuss that motion which is confined to the circular path. Right now, we are concentrating ourselves onto motion which is not confined to the circular path. And the second type of motion which we are going to discuss, the first motion was motion on the outer surface. Motion on the outer surface. The second motion is motion on the inner surface of a circular track. So the heading is motion on the inner surface. Motion on the inner surface of a circular track. Now, what do I mean by that? I hope everyone understands this. I just open this. Up till now, the motion was happening here on the top. Body was moving like this on the top. It was moving like this. Now, what is going to happen? It is going to move in this circular groove. So the motion now is going to happen inside this circular track. Right now, before it was happening outside. Now it is going to happen inside. This is outside, outer surface, inside, inner surface. Now it's very easy to understand that the outer motion can only happen in the top half and the inner motion happens in the bottom half. Now this motion, when we are going to understand this motion, we are going to understand this motion and as well as, so I'll just put a slash, mass attached to a string, or simply we are also going to understand the motion of a simple pendulum. You can also call it simple pendulum, though we will go ahead and do more than a simple pendulum. But both these motions we are going to study under the same heading. Motion on the inner surface of a circular track and a mass attached to a string. And remember, both of these motions are motions not confined to circular path. That means not confined to circular path. That means these gentlemen, whether it is a body on the lower surface or it is mass attached to a string, the motion is not confined to a circular path. Why do I see students leaving? Where are they going? Is there something happening, important happening outside? Where is everyone leaving? May I know? Anyone would like to comment? Where is everyone going? There is no one in the class today? No sir is there in the class to take care of you guys?
Sir,
Yes, beta.
going another class, sir.
Other class means?
In classroom, this is same class going on, sir.
Why? Because they can't see. I mean, something wrong. I mean, I don't see them. So do you have the same class happening in the other class?
Sir, give me 2 minutes, sir. I will back. We are back, sir.
Yeah. Just ask them. I mean, where are they going? And because I will not be able to see them if they go in some other class. I won't be able to see them, and it becomes difficult for me to communicate. So you have the same class happening in two different classrooms?
Yes, sir.
Okay, the first one is the class with the whiteboard. Is that so that I see in the beginning? And then this is the second class, right?
Yes, sir.
Okay.
They are going to that room, sir. 1 minute, we are calling them.
No, I mean, why they are going there? I mean, it's difficult to see it from this class. Is that the case?
Maybe, sir, we don't know.
Okay, not a problem. Chalo. So, in both the cases, whether it is motion on the inner surface of a circular track or it is mass attached to a string, now both the motions are going to be similar. Welcome back, everyone. Are we good to study? I hope.
Yes, sir.
Okay, great. Let us not waste our time onto these activities because these activities can be done later on. Let us now concentrate on what the job at hand. So we are going to study two motions simultaneously. And oops, what is happening here? Okay. Okay. So this, let me call this as case A and this. Let me call this as case B. The blue one and the green one, just to differentiate between the two. Now the blue one is the case of motion on inner surface. This is the case of motion on inner surface. Motion on inner surface. Now what is going to happen here? As you can see, the body to start with will be on the lowest point. In the previous case, it was at the highest point. Okay, I think I got disconnected. I don't know.
Sir.
Okay, I think I'm back now. Just a moment, I'll share my screen. I hope everything is fine. Okay. Are we good to go? Can you all see my screen, bacha?
Yes, sir.
Okay, sorry, I don't know what happened. I just got disconnected and I think I am back now live. Okay, so case A is motion on the inner surface. As you can understand, in the previous case, motion was happening from the top. Right now, the motion is going to happen from the bottom. I have a block of mass M kept at the bottom surface. Now, when it was at the top, I did not give it any velocity. It was just falling down on its own. But when it is at the bottom, if I don't give it any velocity, nothing will happen. So I'll have to give it some velocity. And that is the most important. That is the most important point in this discussion. How much is the velocity at the lowest point? That determines what type of motion this gentleman is going to perform. So I call this point as A, the lowest point, and the velocity at this lowest point, if I give it a velocity, let me call it as VA. This VA is the most important aspect which determines what type of motion this particle is going to perform. Now, my question here is, it has to move in a circular track. Yes. If I draw the free body diagram of this body, the weight mg would be going downwards. The weight mg is going downwards, which is always vertically downwards. We have discussed that. Now my question is, it has to move in a circular path. If something has to move in a circular path, there must be, even if there is no tangential force only changes speed, there must be a centripetal force, because it has to change its direction even if it does not change its speed. Which force is going to give this body the centripetal acceleration? Which force will become the centripetal force? Which force will make this body to move on this circular track? Can you let me know? It is on the inner surface of a circular track. Which force is going to make it move on the circular track? Weight mg is downwards always. It is not going to help in this body move on a circular track. Because of its weight, it will not move on the circular track. Which force will make it move on the circular track? Anyone? And it is not a force which is not visible. You can see it right now. We have drawn it so many times. Which force is going to make it move on the circular track? Anyone? No one knows it?
Tangential force.
Tangential force gives us tangential acceleration. Some force would act as tangential force. I am not talking about the tangential force, beta. I am talking about which force will give it the centripetal force. In other words, I'm just asking you to draw the free body diagram of the gentleman. Half of the free body diagram I have already drawn, beta. You just have to draw one more force and the free body diagram is complete. And once the free body diagram is complete, you will get to know what is the centripetal force. Just tell me.
Reaction.
Yes, beta?
Normal reaction.
Yes, the normal reaction which is coming from this circular track. When you keep it on here on the circular track, this normal reaction will come, which is always perpendicular to the track. This normal reaction at point A, let me call it as NA. This NA will give this body, the required centripetal force. Do we understand this? Can I have raised hand? That we understand this, that here centripetal force, well done, is being provided by the normal reaction. Now let us shift on to the green diagram, which is diagram number B. Diagram number A is what is happening on the inner surface. Now in diagram number B, what I have drawn is I have drawn the center as O, and then I have a string of length L. Instead of here it was radius R. Here the radius of this circular track, oops, wrong color. Here the radius of this circular track is R. I am not calling it as R on the green side because it's a string. So normally we call it length of the string as L. Now I have a small bob of mass M attached here. Now this case B becomes mass attached to a string. I hope that it is very clear and there is no explanation required over here. Yes or no, bacha? There is no explanation required. It is pretty clear from the diagram that this is mass attached to a string. Now again, it is on the lowest point. Let me call this point as point A. Now I give it a velocity VA, and you must understand that this velocity VA at the point A is the most important factor which is going to decide what type of motion. What type of motion? Type of motion is same. What sort of motion, if I can use other term, will this body perform? Now, if I draw the free body diagram of this gentleman, what are the forces I need to draw?
Tension.
I have to draw the tension, which is always along the string, and then I have to draw the weight mg. It is very clear. We have done it 100 times. Now again the same question arises. If it has to move in a circular track, something has to provide it with the centripetal force. Who is going to give it the centripetal force?
Tension provides.
Yes, the tension gives it the centripetal force. So tension gives it the centripetal force, and because of this centripetal force, this body is going to move. Also remember that tension always pulls, so this is pulling it up. Remember, this block is being pulled up by the string, but here on this side, it is pushed up. Do you understand the difference? Pulled up and pushed up. The track is pushing it, but the string is pulling it. Do you understand this?
Yes, sir.
Now, when I do both the cases together, both the cases are absolutely similar. Both the cases are not confined to the circular path. The only difference between the two cases is, which is highlighted in blue, on one side and on green on the other side. So let me call this as tension at point A. So everything looks similar. So the only difference between the two cases is whatever job something is doing on side A, the same job is being done by something else on the side B. What is the differentiating factor? What just makes this question different is because of
String.
string and surface. Basically, if I talk in terms of forces, normal reaction is doing the same thing on left hand side, which is being done by tension on the right hand side. So I will do both of these cases together. Sometimes I may call it as normal reaction. That means I am talking about case number A. Sometimes I may call it as tension. That means I am talking about case number B. Do we understand this? Else, everything else is similar. The entire analysis is similar. Do we understand this? Okay. So let us now just use one diagram, whether it is inner surface of a circular track or mass attached to a string, both are similar. Now, we have to mark some important points in this entire motion. One is point A. Oops, wrong color. I must use blue. One is point A, which is the bottommost point. One is point B, which is like sort of midway. The other is point C, which is the topmost point, and the last one is point D, which is on the other side. Now, if I draw a diameter like this, connecting point B with D, now I can draw the same thing on the other side. Whatever is below this line, will be obviously the lower half of the circle. This is the lower half of the circle. So lower half of the circle is from D to B or from B to D. So the lower half. Whatever is above this is the upper half. Do you understand this? This is the upper part, upper half. And the differentiating line is the line, the diameter BD. Whatever happens below BD, that is the lower half of the circle. Whatever happens above BD, it is the upper half of the circle. Do we understand this? Can I have some reason that we understand this? Everyone understand this? Okay. Now we are going to analyze the motion, and we are only going to use either diagram A or diagram B, because everything is similar in both the diagrams. So I'll give you a minute to write this up till here. Draw the diagram up till here. I'll give you a minute. And I'll be back after a minute. Till then, you can note down this diagram. I hope we are good, everyone. And everyone has noted down up till here?
Sure.
Okay. Let's not disturb the class. I see some students getting disturbed. It's not good. If you don't want to study, you can just keep quiet. I mean, God is there with you. He will help you out. Don't worry. But please, let's not disturb the other guys. Now, let us try to analyze the motion, and let us try to analyze the motion in the way that we have done. So what I do is I'll draw a bigger diagram this time, so that we have more space to work around. Now you can take it as normal reaction, or you can take it as string. Which one should I take? Should I take case A or should I take case B to analyze?
Case B, sir.
Case B. Okay, you might have seen more questions on case B. So I'll take case B, and case B is like this. I have the center here. I have the string here. I am not able to draw a straight line, so I'll just try again. Okay, this looks like a straight line. The length of this string has to be marked as L. So normally what all things are given to you? Normally this length of the string L is given to you. The mass of this block M is given to you. Now what next? Now let us analyze the entire thing. Let us first name these points. This is point A. Then it will sometimes, oops, again I'm not able to draw a straight line. Shameful. Then after some time it will reach point B. After some more time, if possible, it will reach point C. And after some more time, it will reach point D. Now let us draw the free body diagrams at all these points and see what is happening there. So I might use different colors so that you can differentiate. So what are the quantities that we must be worried about? This is VA. VA stands for velocity at point A. Then I have the weight mg going downwards, which will always be downwards. And then I have the tension TA. Now, why I'm using A word here? Because you must understand that at all these points, tension, there are two things that you must be concerned about. One is tension, the other one is speed. Both tension and both speeds are continuously changing. Do we understand this? At different points. From A to B, there are infinite number of points. From B to C also infinite number of points. There are infinite number of points on the circle. As this blob is moving on the circular path in a vertical circle, tension at different points is going to be different. Can I understand this? We all understand this? This is different from what was happening in the horizontal circle. When we had this conical pendulum, tension at all the points were same because the speed at all the points were same. But here, speed at all the points are different. And hence, tension is also different because this tension and speed, they are very closely related to each other. Why I'm calling speed and not velocity? Because I'm more concerned about the magnitude. Direction I've already drawn. Direction is always tangential. So this is at point A. Let me draw the same diagram at point B. Weight mg always goes down. But now the tension T is like this. So tension T is continuously changing its magnitude. It is also continuously changing its direction. Please remember that. The only constant force that you see here, the only constant force which is always constant, we take it as constant. The only constant force is the weight mg, which always remains in the same direction with the same magnitude. If I draw the same diagram, on the topmost point, you will see that the weight mg is going down. At the same time, tension at point B, at point C is also going down. I did not draw the velocity at point B. Velocity at point B will be like this. Similarly, velocity at point C would be like this, and I will not draw the point D because point D is similar. If you want, I can draw point D. Do you want me to draw point D? Point D would be like this. Weight mg would be downwards. Tension TD would be like this, and the velocity would also be in the same direction. I will call it as VD. Do we all agree on this? Can I have some raised hand? Let me understand this. Okay, so far so good. Nothing has changed. I have changed absolutely nothing. Just drawn free body diagram. Now what I'll do is I will write equations. And let us start from point A. Equations at point A. Equations at point A. I have to write equation in three directions. Now remember, the first direction is the tangential direction. The second direction is the radial direction. And the third direction is the perpendicular direction. Is there any force in the perpendicular direction on this body? Whether it is at point A or point B or point C or point D, is there any force in the perpendicular direction?
Point A tension.
There is no force in the perpendicular direction. So, because there is no motion happening in the perpendicular direction, so there is no force in the perpendicular direction, we don't have to write that equation at all. So, we'll not write that equation. Then what is the first equation that we write? And I shall use which color? I will use black color. Or I'll use blue color, yeah. What is the first equation that we write? For point A, what is the first equation that we write? The first equation is along the tangential direction. Do you see any force in the tangential direction? Do you see any force in the tangential direction? There is no force. Yes? VA cannot be force. Bacha. VA is velocity. How it can be force? Okay, there is no force in the tangential direction, so Ft is 0. Do you all understand this? VA is the velocity, it is not force, beta. I cannot make velocity as force. Okay. Can anyone tell me what is the second equation here?
Centripetal, sir.
Can you tell me the equation? How will the equation look like? How will you make the centripetal equation? You don't know how to make the equation? Centripetal equation towards the center.
TA equals to VA square by R.
What about mg? You forgot an mg. Okay, so the equation will be like this. F centripetal, you have to find F centripetal. Towards the center, what is the force? You can see one is TA and you can see one is mg, which is downwards. So you will have to subtract TA minus mg will be equal to mva squared by L. Do we all understand this equation? Do you all understand this equation? Yes or no?
Yes, sir.
Okay, that is equations at point A. There is no perpendicular force, so I will not write any equation in the perpendicular direction. This is what my point A key equation looks like. Now we come to point B. Now we come to point B. Again, the perpendicular force at point B, which is perpendicular to the plane of the paper, equation number 3 does not exist. Now I will write the first equation in the tangential direction. Now, since I want to continue the same sequence, because I will be using the same sequence, I will call this equation as equation number 3. Why it is equation number 3? Because 1 and 2 are already above. So what is equation number 3? This equation number 3 is the equation in the tangential direction. What is the equation at point B in the tangential direction? Tangential direction is a direction which is tangent. The velocity is also tangential. What is the equation in the tangential direction? Can anyone tell me?
MG, sir.
Yes, the tangential force, Ft. Tangential force is mg, and we must also write its direction. It is downwards. Tangential force is mg. Direction is downwards. Now, as you can see here, and please open your eyes, that this velocity at point B and this weight, velocity at point B is upwards, but this weight or tangential force is downwards. Something is moving up, but something is trying to pull it down. What will happen to the velocity from A to B? Will the velocity increase or will the velocity decrease? The velocity will keep on decreasing. The velocity is upwards, weight is downwards, so it will try to decrease velocity. So instead, if I just use the symbol, that sign convention, that upwards is positive and that downwards is negative, if I use that symbol, upwards is positive and downwards is negative, I can call this weight mg as negative. Here also, if you can see, we have called this weight as negative. Yes or no? I can call this as negative, but you know that it is downwards, so you don't have to say anything else. From here, you can find out the tangential acceleration. This ft is mass multiplied by at. So from there, you can calculate the tangential acceleration. How much is the tangential acceleration at point A, at point B? Please tell me. How much is the tangential acceleration at point B from the equation? And the answer is, it is g in the downward direction. Do we understand this?
Yes, sir.
In the first case, if I would have asked you what is the tangential acceleration at point A, your answer would be simply, it is equal to 0. So far, so good. We are doing absolutely fine. But now we have to bring our attention to point number 4. The point number 4 or equation number 4 is the equation in the centripetal direction. And now someone has to tell me what is the equation in the centripetal direction at point B. What is the equation in the centripetal direction at point B? Someone has to come up with an answer, a convincing one also.
Cb equals to mvb square by L.
Yes. Now see, all of a sudden weight has disappeared. Weight is nowhere. It's only tension that we must be concentrating on. So this is tension at point B is equal to m into Vb square by L. Do we all understand these equations? Why there is so much of unrest in the class today? Why are you not able to keep quiet? I have been giving examples of this class to other students, that my class in Hyderabad is very disciplined. And these guys, very proud of these guys, that they sit very patiently in the class and they are very attentive. But right now, it seems that I would have to change my opinion, and I would have to put you in the same category as normal students are. In my class, they are not. But since I'm not available, say they are. Because in my class, if someone just moves, I just throw him out. You move out. You move like this, you move out of the class. And stay in the class and keep on moving. I don't like dances in the class because this is not a dance academy. And I don't like motion in the class. The only motion I like is the motion of your hands and your eyes and your brain. These are the three motions that you do in a class. Any motion like this has to be done outside the class, where everyone can see you and appreciate your dance performance. Let us not create this into a dance academy. This is a classroom. Point number C, we come on to. And F perpendicular is 0. There is no force in the perpendicular direction. So let us not worry about this. Let me move on to equation number 5. I am naming this equation because I will be using them in the next class. 1, 2, 3, 4, 5. So you also name them in the same way. What is equation number 5? Equation number 5 is the equation in the tangential direction at point C. Can anyone tell me what is the equation?
Ft equals to 0.
Yes. as you can see, ft is equal to 0. So now we are getting the hang of things. Ft is equal to 0, which implies tangential acceleration is also equal to 0. What is you got to note here is tangential acceleration is continuously changing. Tangential acceleration is continuously changing. It is changing in magnitude as well as it is changing its direction, and therefore the equation, the motion becomes very complicated. Very complicated. Centripetal acceleration is changing also. Changing in magnitude, changing in direction. If I write the equation at point number 2, equation number 2, it will be equal to m into AC. So centripetal acceleration at point A is VA square by L. Centripetal acceleration at point B will be VB square by L. It is also changing magnitude. It is also changing direction. So both the centripetal as well as tangential acceleration, they are changing their magnitude, they are changing their direction, and hence this motion becomes very difficult to understand. But we'll try to understand it in the simplest possible language. Let us move on to equation number 6. And who is going to tell me equation number 6?
TC plus mg equals to m v square c by L.
Yes. Now I have tension at point C and mg both joining hands. Both are coming in the towards the center. TC plus mg, that should equate m into vc square by L, and that will be equal to m into AC, which is the centripetal acceleration at point C, which you can see has again changed its magnitude as well as changed its direction. Are we all in unison here? We all understand this, right? Yes or no?
Yes, sir.
Great, great. Well done, well done, well done. Now let us move on. The only point that is left right now, there's also one more point left. I will be doing that point as well. Now we move on to point number D. Fatafat, tell me the equation at point number D. The first equation I will write. F perpendicular is 0. So you don't have to worry about that equation. There is no perpendicular force. Let us move on to the equation number 7. Who will tell me equation number 7 at point D, which is the equation in the tangential direction?
Minus mg.
Yes, so instead of writing it minus, you can just write it downwards. Mg is always downwards, it is always minus, my dear friends. It is never plus, it is always minus, it is always downwards. Upwards is positive for us always, downwards is negative for us always. So mg is going to be negative always. Mg in the downward direction, I can also call it minus mg. This implies my tangential acceleration again would be equal to g in the downward direction. That takes me in very short time. Well done, boys. On to equation number 8, which is the equation of centripetal direction. What is the equation of centripetal direction? What is the equation in the centripetal direction at point D? No one knows the equation?
TD is equal to mvd square by L.
Yes, TD is equal to m into Vd square by L, and that will be equal to m into AC, centripetal acceleration at point C. Does not stand for point C. C stands for centripetal acceleration. Yes, Santosh, you are also there in the class. Well done. M into Vd square by L. That is absolutely correct. Now comes one question that, not one question, just one more case. I've only taken 4 points on the entire circle. You will say, sir, these are not the only points on this circle because there are infinite number of points on this circle. Yes, I agree that there are infinite number of points on this circle. I will take one of those points. Comes my next hero. My next one is here, point E. Now, I've taken 1 point between A and B, and since I am very symmetrical and I like symmetry in my life, since I like symmetry in my life, I have taken one point E between A and B. I can take a similar point F between B and C. I can take a similar point E, F, G. G between C and D. I can take a similar point H between D and A. If you understand any one of these or any two of these, for example, E and F, you should be able to do all the points in this wonderful universe of ours. Now, once you have this point E, you must know the location of this point. Now, how do I tell you the location of this point? I will tell you in terms of this angle theta. Now, remember, in vertical circular motion, wherever any angle is given, whenever any angle is given, it is always given from the vertical. And that is why I have given you this angle from the vertical. So right now the angle from the vertical is theta. This theta could be anything. Similarly, for point F, I am making this angle as phi so that you differentiate that one is theta, other is phi, so it is different. Now what you got to do is you have to write the equations at point E and point F. At point E and point F, you have to write the equation. You will start with point E and tell me, sorry, tell me what does the equation at point E looks like. What does the equation at point E looks like? F perpendicular is 0, so I'll do that part for you. F perpendicular is 0. Now, can you write the equation at point E? I'll help you out. What is the first thing that you have to do?
Set
To write?
TA cos theta.
Yes, beta?
TA cos theta.
Let us first draw the free body diagram. Let us first draw the free body diagram. Weight mg, as always, is a very disciplined student, just like you guys. It does always stay in the same position. It always acts vertically downwards. My tension at point E, this is somewhat notorious, but it has to do its job. So it has to keep on changing. So it keeps on changing. Right now it is like this. And the velocity at point E is always tangential. So this is velocity at point E. Now, my dear friends, the baton passes on to you to let me know what are the equations here. Remember, something has changed. This is my radial direction R, and this is my tangential direction T. So I've drawn R and T. I hope you can see that. My lines are not straight, but my heart is. R and T, radial and tangential. Can you give me the equation in the radial and the tangential directions, bacha? Can you? Or can you not? So this is the task for you. I can do it in 1 second. I can just write the equation in 1 second and done with this. No, but that is not what I want you to become. I don't want you to become what we call kagas ke sher, lions who are only lions on paper and they do nothing on ground. They just keep sitting and snoring. I am lion, so everything will come to me. No, if you're a lion or lioness for that matter, you'll have to go out and hunt. If a lion cannot hunt, he is of no use. You can't be the king of the jungle. So wake up. That's a home task for you. You have to write the equation at point E. Once you are done with point E, then you will have to move on to point F. Once you are done with E and F, that would settle the issue because I don't need G and H. Hardly they come in. Once you know E and F, E is in the lower half, F is in the upper half. Similarly, H is in the lower half and G is in the upper half. You should be able to make the equation for G and H. You have to make the equations for E and f. That is your home task. Do it and let me know the equations. We will begin the next class with this class. So whenever you are coming for the next class, please, 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 please see a recording of this lecture. Study what we have done in this class so that we can begin the next class and wind this thing up and there itself. That's it from my end. I hope you have loved this class and I hope that you will be attentive in the class as always. And we will be doing some wonderful questions on this so that this concept becomes clear. So class is over from my end. Stay safe, stay healthy, stay happy. Take care. Bye bye.